sequences, we need to talk about convergence theorems. Being able to compute a limit directly for a sequence is essentially the same as computing the limit of a function. And that isn't too bad. However, we have practiced writing down these closed form expressions, these solving for the general expression. However, not every sequence can be written with a formula for general term. So that kind of poses a problem. And if a sequence can't be written in such a way, well, how do I find limits? As well, we've also seen some extra functions we're introducing, these factorial functions, these alternating functions, which are a little bit different than the standard base of functions that we've developed in pre-calculus and calculus. And so now we got to also be able to take limits of these factorials and learn how to deal with them. And sometimes the typical sort of limit methods that we've done from pre-calc and calculus won't work for those. So other tools we have, one is called the absolute convergence theorem. This one's not too bad. It's basically absolute convergence theorem. Basically, it means if the limit as n goes to infinity of the absolute value of a sequence exists, then the limit as n goes to infinity of the general term exists. This is useful for dealing with alternating sequences. So for example, if we want to find the limit as n goes to infinity of minus 1 to the n over n, well, I know that if I take an absolute value, well, the absolute value of minus 1 to the n, since minus 1 to the n is just going to give values of minus 1, 1, minus 1, 1, then this sequence is just going to be 1 over n. And so since this limit exists, and I didn't need the absolute values there. It's just 1 over n now, since our n are positive numbers. Then the limit of an alternating sequence exists. I will make a note to just be careful in this case with the absolute values. The only reason I can conclude that this limit is the same, I know that, I guess, so to do it proper, I know that since this limit exists, I know that this limit exists. How do I know it's 0? Well, really because of the fact that if it converges an absolute value, then the limit of the original sequence is going to be essentially plus or minus the value we get. And since it's 0, plus or minus 0 still gives me 0. So since it converges to 0 in absolute value, it will also converge to 0 for the original function or the original sequence. This is also a consequence of the next theorem, which is the squeeze theorem. And I think you guys have probably seen some version of this for functions in Calc 1. So what does the squeeze theorem say? Squeeze theorem tells us that if we have some sequence, let's call it an, if it's bounded by two other sequences, say, let's say we have bn is always less than an, or it could be less than or equal to, which is less than cn. So our an is bigger than one sequence, less than another, and the limit as n goes to infinity of bn is some finite limit, which is also the limit of cn, then, well, I know if I, in some sense, if I take a limit to infinity of this whole inequality, this guy has to be L, this guy has to be L, the middle term has to be L. And let me write that out. So let's just finish the statement of the theorem. And then let me kind of write out that shorthand. Essentially, it's this. If we apply the limit here to our inequality, since this inequality holds for all n, then it has to hold in the limit as n goes to infinity. And now essentially all we're doing, since bn and cn converge to L, then, well, this limit, the limit of our original sequence, well, it has to be less than and bigger than L, so it has to be equal to L, is the idea behind that guy. Anyone still writing? Okay, so let's see an example of that. We should say find the limit if it exists. And we've got the limit as n goes to infinity of n factorial over n to the n. So this will give us some practice of dealing with these factorials. So I can't model this with a function. This one would be x to the x, which you've probably seen maybe once or a couple of times in Calc 1, maybe with L'Hopital's rule or logarithmic differentiation. And n factorial, as we've seen, we don't really have a nice way of modeling it as a function. It would be a complicated function that's called the gamma function, which you usually won't get into unless you take like discrete math or analysis. So we have to kind of just use some algebraic tricks to find this limit. And so let's consider terms of the sequence and try to see what's happening. When n equals 1, we're just going to get 1 factorial over 1 to the 1. Our next term, we will have 2 times 1 over 2 squared, or 2 times 2. It's helpful often with factorial, especially if you're writing out the terms, to simply write out the product, similar with n to the n. Because with these ratios, the trick that we're going to ultimately end up doing is kind of comparing consecutive ratios. So we've got n equals 3. What is that going to be? 3 times 2 times 1 over now 3 cubed, 3 times 3 times 3. And likewise, let's do one more. 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. So what's happening with this guy? Which one's bigger, the numerator or denominator? Should be clear that the denominator is bigger. The first terms are always the same, but then as the terms decrease in the numerator with each successive product, the terms are going to stay the same in the denominator. And so what you consider is, let's kind of mess around with this general term again. So we've got n factorial over n to the n. Factorials are kind of a funny thing. Because n factorial is n times n minus 1 times n minus 2 all the way down to 1, n to the n is just multiplying by n that many times. We can kind of see of what's going on here, that this first term is always going to be, the ratio is going to be 1, but this guy is always less than or equal to 1. So let me see. So if we replace that guy, I think we might need to pull out an extra term here. Yeah. Oh, so that's not going to quite help us. So let's see. We want to claim that it converges. The problem is here. So this guy's less than 1. I actually kind of group my terms a little bit weird. Let's write it like this. So that's our numerator. Our denominator's here. Just a bunch of n's. We want to consider this chunk. So this guy's not wrong, though it doesn't help us. What did we just show here? Well, we can essentially show that the general term is always going to be less than 1. But a sequence that's constant 1 might converge. Well, it'll converge it to at most 1, but we also need to find a lower bound for this guy to use our squeeze theorem. So let's write down some of these thoughts that I'm trying to formalize. We want to use the squeeze theorem. There's no minus signs here, so I know that this sequence is always bigger than 0. From looking at the sequence, well, I know that the bottom's always going to be bigger than the numerator. And in particular, if you kind of look at these n terms, well, this is like 1 over n. And as 1 over n goes to infinity, it's going to go to 0. Likewise, this 2 over n going to infinity is going to go to 0. These terms up here, well, n over n, that's going to go to 1. But still, we'll have something like 1 times 1 over infinity. So we should suspect that it goes to 0. So really what I want to do is, instead of bounding this by 1, I want to be able to bound it by a sequence that will ultimately go to 0. In other words, because of all of these terms, all of these first terms, n over n, n minus 1 over n, I know that this whole product is less than 1. So meaning my original sequence is always going to be less than 1. I'm replacing this whole chunk with that 1 times that last term, times 1 over n. So I just put this guy there, and then this guy there. And of course, they're being multiplied, so we still get a product there. And so because we have this inequality, we can take the limit and going to infinity of, 0 is less than the limit as n goes to infinity is less than or equal to the limit as n goes to infinity. 1 times 1 over n, or just 1 over n. And now when I compute the end limits, well, what do I get with this piece? I'll get 0 here. This is just a constant function. So think of this as just a horizontal function, right? Y equals 3 or something like that. In this case, y equals 0. And instead, it's a sequence of 0, 0, 0, 0, 0. And this limit was the limit we wanted to compute. And now this limit is going to go to 1 over infinity, which is also 0. So by the squeeze theorem, the limit of our original sequence is 0. Any questions on that? We can do some more of those as we get going, especially with manipulating these factorials. It takes a lot of practice. Sorry, what was that? Was there a question? Or was that just background noise? Background noise? Okay. So we want to talk about increasing, decreasing sequences. Monotonic. These, I just want to go through real quick. It's the same as increasing or decreasing functions. So a sequence is increasing. So think of if the next term, so whenever I put a subscript as an plus 1, think of that as if the next term is bigger than my current term, an, that means we are increasing. Of course, this has to hold for all n. If an plus 1, if my next term is less than my current term, for all n, decreasing. Monotonic just means it's one of these guys. So how do I check if a function is increasing or decreasing? We can either do it explicitly using some sort of sequence notation like this, or we can essentially use our calculus tricks. So let's say show that an is n over n squared plus 1 is decreasing. So practice a n plus 1. Think of this n plus 1 as substituting, instead of f of x, we have f of the quantity x plus 1. And so there we want to put an n plus 1 in for all the n's. And we want to compare that to an. Excuse me, that's a 2 there. And so we just want to claim that this guy should be smaller than that guy. And let's see, so sometimes this method works, sometimes it's a little difficult. The denominator is bigger, but the numerator is also bigger. So a bigger numerator makes it bigger, but of course a bigger denominator makes it smaller. Bigger denominator, the denominator key thing there is it's being squared, so it will ultimately be smaller. The question is, can we deduce that with just by comparing the algebra on this guy? Let's see. So we might have to square that out. Or we might be able to. Usually what you want to do is to try to manipulate this guy to figure out if we have a term like this, we can kind of pull out in some sense. And it doesn't look like we're going to be able to, because our best option here might be to FOIL this guy out. But then foiling it out isn't going to give us a good sense of how to compare it with that. We can try. So let's take a look. So let's do some scratch work. We want to manipulate this guy around a little bit. So about the only thing I'm seeing is to try to FOIL things out. So we'll have a +1 is a +2. And so what's that going to be? This is going to be n plus 1 over, and actually let's write it n squared plus 1 plus 2n plus 1. So keep that 1 plus 1. And the reason I want to compare that is I want to compare these denominators. And let's see. So this is a smaller denominator. We want to get this guy as less than that guy. And so we essentially need to make an argument that this denominator is growing bigger than the numerator. And that this guy is going to be less than that. Yeah, that's going to be a little difficult to argue. So I don't know if this method's going to work. Our other method to do. Ultimately, I want to be able to compare. We want to be able to say this inequality. And so just like our comparison tests we have been doing, if this denominator is bigger than this denominator, I can conclude it. The problem is that this numerator is bigger than this numerator. So without doing some more advanced analysis on this, we can't do. So we can't do only based on a numerator and denominator comparison, at least at the moment. We would have to do a little bit more work, a little more algebra, analysis to get a little more technical with that. And I don't want to spend too much time on that, because the other thing we can do is just consider our function f of x over x squared plus 1. This function matches the sequence on all integer values. And so if I can just show that this function is decreasing, by analogy, the sequence has to be decreasing always. So how do we show something is decreasing? We take a derivative. So f prime of x, and of course we only want to consider x values from 1 up to infinity, since that's essentially where our n's are going to lie. N's are going from 1 to infinity, but just integers. Take our derivative, so we've got bottom, derivative of the top, minus the top, derivative of the bottom, all over the bottom squared, and simplify. So what do we have? X squared plus 1 minus 2x squared over x squared plus 1, which is going to equal negative x squared plus 1 over x squared plus 1. And now on that domain, if I plug in 1, so of course at 1, f prime of 1 is 0, but for all x bigger than 1, f prime of x is less than 0. Does everyone see that? So if we kind of consider this function, what's happening? I know that at least at 1, my function is going to have a specific value, and it's kind of like a peak there, but that 1 point doesn't quite matter, because all successive points after that, I know that the derivative is negative. If I plug in 2 here, it'll be a 2 squared. Negative will give me negative 2 squared plus 1. The numerator will always be negative. The denominator is always positive. So overall, the derivative is always negative. So f of x is decreasing, which implies an is decreasing. Questions on that guy? So increasing, decreasing. I do encourage you to try to play around with the algebra a little bit to see if you can get a comparison, just because practicing this comparisons, we're going to be doing this for a little while. Comparison tests kind of show up with all of these sequences and series. And so just being able to, write inequalities and comparing sequences, series, good practice. And then if you can't see a necessary algebraic manipulation, we can always do a little bit of calculus tricks from Calc 1. So I'm going to X that out, because we have that comparison, but only by our calc tricks. It's not as clear from there yet. Okay, the last thing I want to talk about with sequences are recursive sequences. And these are the types of sequences where we often cannot write them in a nice general expression. Sometimes we can, sometimes we can't. But regardless, we want to be able to take limits of something like these. So what is a recursive sequence? A recursive sequence always gives some sort of initial value or you can call it a starting value, or a seeding value. And then what does it describe? It describes how the next term relates to the previous term. And actually, let's call it the current term. So given our current value, our current term, I want to know, how do I find the next number in the sequence? I plug in my current term to this formula, and then I get the next term. So we have to start somewhere. So I know that A1 is just going to be 2. How do I find A2? Well, A2 is going to equal 1/2 A1 plus 6. So 1/2, we plug in A1 to that guy, and we get a value. How do I find A3? We just keep going. A3, so 3 is 2 plus 1, which means I need A2 there. And so A2 was 4. And we get 5. Let's do one more. A4 is 1/2 A3 plus 6. So everything, hopefully everyone can kind of see, right? Whatever my n is here, so if n is 3, then that will give me the result of my fourth term. So these should always differ by 1, because that's what it's dictated by our recursion formula. So we continue to fill in. A3 was 5, 1/2. 5 plus 6, and we get 5.5, or 11 halves, if we want to keep fractions. And so if I were to list these numbers out, we may not be able to find a nice closed form expression of this, a nice general term for an. But we might want to find the limit. How do we do that? Kind of like what we were doing with the squeeze theorem when we have these comparisons, these greater than or less thans. If I have this expression, an plus 1 is equal to 1/2 an plus 6, this has to hold for all n, which means if I take the limit of both sides, the equation still has to hold. An plus 6. And now, well, what's going to happen? As we go off to infinity, the limit of an plus 1, if the limit exists, this is just going to go to the limit of the sequence. So suppose the limit exists, and we're going to call it out. So whether I start at the next term or the current term, as the terms get bigger and bigger and bigger, they're both going to go to that limit. Likewise, over here, these an terms, if there's a limit to the sequence, these an terms will go to that same limit. And so if the limit exists, it must satisfy this equation. Well, let's see if we get a finite value out of that. So not every limit will exist. Sometimes you will find the limit needs to be infinity. There might be some fancy algebraic operations there where you end up dividing by 0 or something. And if we solve, though, if I subtract off the 1/2, we realize that the limit satisfies 1/2 L equals 6. And so L should ultimately equal 12. Any questions on that? One second, let me check something. I feel like the limit should be 6. I just want to make sure I didn't like miswrite things. Because when I take a limit of both sides, we'll get L and L. And when I subtract 1/2 L equals 6, yeah. The problem is what's my next term? If we check numerically, we will have 5.5 plus 6, which is 11.5 divided by 2, which is 5.75. And I feel like as the ends get bigger, we should only approach 6. I did some algebra weird somewhere. Let me see if I can find it real quick. Then we can get started on the quiz. Does this process make sense, though?
Yes, it's pretty straightforward.
Yeah, taking the limit of both sides, you get your L's, and then you should get a nice equation for it, and solve for L, and then it kind of just pops out. Let me see if I did something wrong real quick. Oh, that's what I did wrong. I didn't distribute. Derp. Got to distribute that 1/2. So 1/2 times 6. That ends up being a 3, and that ends up being a 6. So just rushing through the algebra a little too quick there. Okay. Let's do one more since we got about 10 minutes. Just for these recursion sequences. So suppose we have a sequence that looks like this. This one's a little trickier. And it's going to keep going. So we want to find the limit if it exists. This one's weird, right? How are we going to model this with a function? It's going to be really, really hard to do. And finding a closed, like a general form expression for this is going to be hard. So let's try to think if maybe we can model it by a recursive sequence. First term is square root of 2. And what I need is a formula for how to get the next term based off of the previous term. And the thing I want you to think about is, well, here I have a square root of 2. You want to think of that square root of 2 as living sort of on the most inside for that next one. So if I consider this as my first term, how do I get the next term? I would take this first term, multiply it by 2, and then take a square root of that. So let's check. Should that work? So if that's my A1 and this is my formula, what should A2 be? A2 should be square root of 2A1, which is square root of 2 times the square root of 2. A3 is square root of 2 times A2, which is square root of 2 times square root of 2 times the square root of 2. So a little tricky with this guy, but the formula ends up working there. So if you're having trouble finding a general form, practice coming up with these recursive formulas for your sequence. And then what we want to do is take the limit of both sides we replace any of the ANs and AN plus 1s with L's and then solve for it. So if I square both sides, we'll get L squared is equal to 2L. So L squared minus 2L equals 0. And our limits either our limit is 0 or the limit is 2. In this case, what should the limit be? You would have to make an argument as why it's not one and the other. You could show that, well, since A1 starts at 2, then the next term is actually slightly bigger. And then the next term is even slightly bigger than that. You could show that it's increasing, and so that it will never decrease and never be 0. Or argue somehow similarly. So in this case, our limit is 2. Any questions on those? Okay. So go ahead, put away all your notes. And if you want, go ahead and sign on to Canvas. It's 11:45, so the quiz should be open. And go ahead and get started on that. It's a written quiz, so you'll have to handwrite it and then scan it and upload it into Canvas.